All right, let's let's just get started. Welcome back, everybody. Welcome to the new uh 312, the new UB, the new world it is, as it seems. Um, as I just break everything in, let me know if there's anything with the audio, the video. I do have my face cam for those of you who wanted that. So what's up? And let's jump into things. So the first thing I want to talk about, Project Phase 2 is up. I don't want to talk about this too much, but I just want to highlight that it is here. So Phase 2, it is, as I advertised before, it's everything that you can do without building user accounts. So we're starting to get some of the functionality of the website. So all the functionality that we can get without needing user accounts, which is a lot of the first 3 bullet points, under the assumption that with the user accounts bullet point, that every user is the same user. So build everything as though everyone is logged in as the same exact user. So we can kind of get this first bullet point. It won't make a whole lot of sense until we get to phase 3. But the next 2 bullet points, we can do this quite well. People sharing multimedia content, voting on that content, and voting on that content and commenting on that content. Let me adjust the audio a little. And then the next 2 bullet points don't make sense until we get to phase 3. The being able to follow users and being able to DM other users. Those don't make sense. If we only have one user account, what does it mean to DM yourself? So I highly advise that you think about phase 3 as you're building phase 2. Phase 3, where it's going to be the rest of the app. Adding in those user accounts will be the big thing. Handling user passwords, securing those, and building the rest of this functionality that you need specific user accounts for. So please keep that in mind as you're building phase 2. Don't back yourself in a corner where you have your project architectured in such a way that adding user accounts becomes impractical or infeasible. You might end up in a situation where you're rewriting your entire program. So just think about the user accounts as you're building these features. It'll save you a lot of time in the next phase. We do have a little bit of security concerns here. Since we are taking user data and sharing that with other users, we have that concern that we had on the homework of HTML and JavaScript injection. So making sure that you're watching for that and protecting against that. That's one thing we're going to check as we're grading. And also SQL injection if you're using a SQL database. Just making sure that users can't get into your database, can't steal other users' data, and can't inject their own SQL data into your database, which we'll talk about next week more in depth. This is going to come down to using prepared statements. I don't expect you to get more advanced than that, but if you're not using prepared statements, we're going to find that and we're going to penalize that accordingly. These are both pretty serious security flaws that can completely take down your app, can compromise all of your user data. So the consequences could be pretty strict, especially if you're vulnerable to HTML and JavaScript injection. It basically means you haven't paid attention much at all to security. So that could be a 0 on the entire phase of the project. So please be sure you're watching for these security flaws. And then for phase 3, there's going to be a lot longer list of security. This is one of probably the most important topic when building and deploying web apps is security. You don't want to make the news. You don't want to have headlines. You don't want to put your company on the headlines because you have a big data breach. You want to make sure that you're securing user data when you're handling that data. So this will be a bigger focus as we start handling more and more sensitive information as the project goes on. And for Docker, we'll use Docker Compose because we also need a database for this one. And again, we'll talk about that next week as we talk about databases. And as always, we had lecture in class, so you could always just shout out questions, but now we have to rely on the chat. I'll be keeping a closer eye on chat than I have in the past. I watched it pretty good anyway. But I'll be watching the chat for questions. Right now, it's just a few of you saying the stream looks good, so I'm happy about that. I can adjust the audio levels too, so if the audio is off, just let me know. I can't really, it's hard for me to tell these things from where I'm sitting. I can just look at the bar go across the audio. Audio is fine for me. Awesome. Audio is perfect. All right. I like it. Let's we might have a pretty seamless transition here. Let me check one thing. Okay. All right, homework 7. Homework 7's out. This I gave some warnings earlier in the semester that homework 7 and homework 10 were going to be the big tough ones. I'll say that's no longer true for homework 7. I did nerf this quite a bit. I wanted to make this more involved, but I didn't have a good way to do that without making it ridiculously involved. And then so I was on the fence on that already. And then with all the changes with being online only and just the logistics are going to be a little tougher, getting time in office hours, etc. The assignment's quite a bit easier than it would have been. That doesn't necessarily mean it's easy. For some of you it will be, for some of you it won't. And let me explain that in a second. So we're going to add HTTPS to our sites. We're going to use encryption. You're going to generate your own certificates and add those certificates to your site and encrypt all of the traffic going back and forth. And objective 2 is here. I would ignore this one off the bat, redirecting your HTTP traffic to HTTPS. I would ignore this off the bat and jump right to objective 3. Objective 2 is only there if you can't figure out the rest of the objectives. If you can't get HTTPS working, there's an opportunity for you to get 3 extra points for objective 2, just in case things go wrong. So a lot of this, so you're allowed to use any library that you want to be able to get HTTPS, not HTTPS, but TLS up and running. HTTPS is HTTP over TLS. TLS is a security layer. We'll talk about this all this week, but let me give a quick overview. TLS is a security layer that's right in between HTTP and TCP. So if you can add TLS to your TCP sockets, you can use your entire website that you've already built, your entire server that you've already built, and just use the TLS TCP socket stream as though it were a regular TCP socket stream. So for some of you, depending on your language and framework that you have set up, there will be a pretty straightforward way to generate your certs. There's a straightforward way for all of us to generate our certs, which we'll talk about Friday. I'll give an example of that. But there might be a very easy way for you to add those certs to your TCP stream, to your TCP server. And if there is, you can add those certs and get those added. A lot of that's going to be finding documentation, reading through that documentation, figuring out exactly what you have to do to be able to get that to work, to install those certs into your stream. But you can use any libraries you want. You can use any built-in SSL or TLS libraries to be able to get those certs installed on your server to have your TCP stream encrypted with TLS, and then you can just hook it up to your existing HTTP server. The whole goal of this is to reuse all of the HTTP code that you've already written, and add a layer of security on top of that. This is how HTTPS was designed. HTTPS was designed to just use HTTP as is and just add that security on top of that. So that's what we want to see in this homework, how we can just add a layer of security, add encryption to our server without having to rewrite and restructure our entire app. SSL and TLS are effectively the same thing. I mean, they're different. They're different but the same. SSL, there are 3 versions of SSL which get just progressively, I'll say, better. As vulnerabilities are found in a certain version, they'll come out with the next version, patch all the security, make any improvements that they can. When they got to version 4 of SSL, they renamed it TLS. It was just a name change. So SSL, TLS, if you see SSL and TLS, they're pretty interchangeable. TLS is just the new name. But a lot of the libraries kept the SSL name. Like in Python, you'll be somewhere in your documentation, you'll find that you'll need to do import SSL, but it will actually implement TLS. It was just a name change that they had at some point. The current version is TLS 1.3. But in some of our examples in the documentation I linked to some TLS 1.2. There's some changes for efficiency in 1.3 and a few vulnerabilities that they found, which I might talk about. But it's just newer versions of the same library. And we do have a bonus objective. This was going to be part of the original objective, getting WebSockets, secure WebSockets. Once you install the cert, your TCP socket is going to implement TLS. If you already have your WebSockets working from Homework 6, they just basically become secure WebSockets because you were securing at the TCP layer. Your WebSockets just use that TCP socket. So if that TCP socket is now secure, your WebSockets are secure. No extra work to be done. You just got to go into your front end and add an extra S to the WS. Make it WSS. Done. The reason this is a bonus objective is because I didn't want what we call cascading failure. If you weren't able to figure out Homework 6, I don't want you to also be punished on Objective 4 of Homework 7, because this is just going to be Objective 4. But I want to get rid of that cascading failure, so I decided to just have it cascading success, I guess. If you got Homework 6, you'll get some extra bonus on Homework 7. If you didn't get Homework 6, you can still work on the Homework 6 to get the bonus to be able to make up some points. Make up some points elsewhere. All right, let's... where am I here? Let's get this out of the way. Let's take this. Full screen. All right, any other questions before we get into this? Okay. Let's talk encryption. All right, so we have a big problem with our apps that we built so far for the homeworks, for the servers that we've built, is that we're using only HTTP. And all this information that we're sending this over TCP sockets, and we're sending it in what we call plain text. It's not necessarily text, but it's just out in the open where people can see it. Anyone with access to the network can see what we're sending. They can just they can pull those bytes, read them, follow the same protocols we're following to figure out what these messages say. And the people with access to this are anyone on your ISP. If you trust or don't trust your ISP, that may be a big difference to you. UBIT on campus, everyone maintaining those networks, all the employees for UBIT, anyone work on those networks. Any of the Tier 1 networks, we briefly talked about these in week 1. The Tier 1 networks are the organizations that your ISP and that UB pay for their network access that plug us into the whole the internet at large. They effectively make up what we call the backbone of the internet. And then your ISP is solving what's called the last mile problem, connecting your specific house, to the Tier 1 networks, to that backbone. The ISPs are only regional, where the Tier 1s are effectively global. So depending on your level of trust, that might not be a big deal for you. You might trust your ISPs, UBIT, Tier 1 networks. The people whom you should not trust, whom nobody should trust, is every single person within Wi-Fi range of your device. Anyone within Wi-Fi range can read these packets that we're sending. They can tap into those TCP streams, those TCP sockets, and read every single byte that we're sending over those. If you're on Wi-Fi. So if you're on Wi-Fi, we have a wireless access point that you're connected to, and this is the point where I'd look around the room and look for a Wi-Fi signal and point to it and be like, that, you're connected to that. Anyway, you have to imagine that part. But the Wi-Fi and the Wi-Fi network cards in our computers, in our devices, and the Wi-Fi access points, they don't know where each other are. There's no sense of location here. So what they do is just broadcast the signal in every direction. They're omnidirectional antennas and broadcasters. So when you send out a message to that Wi-Fi, to that wireless receiver, you're just sending it in every direction, which means everybody else in that range of that signal can pick up that signal, read it, and see what you're doing, can read that message. If we're using HTTP and not HTTPS, which of course will be our answer here, if we're using HTTP, everyone can see exactly what you're doing on the internet. They can read every byte of every message, everything that's happening, which is a huge privacy concern. So we don't really like that. If you don't want everybody in your business, this is something you should not, that you should definitely not enjoy. So the solution is going to be HTTPS. I would imagine you've all heard of this at some point. It's that lock in your browser. If you see that lock, you have HTTPS, which is pretty much every website these days. Google took a pretty hard stand with Chrome. And if you connect to an HTTP site these days, Chrome will give you all kinds of warnings and stuff and say this connection is not secure. Once Google made that change in Chrome, it pretty much forced any website, any developers who were not using HTTPS yet to switch over to HTTPS. So those warnings scare users. You don't want to scare away your users. This is pretty ubiquitous now. So let's talk about what this is. It's and this is going to, of course, be the topic of the whole week. So today we want to talk about public key encryption and also certificates. Oops. Whoa. Scrolling the mouse wheel changes my slides with this program. TIL. So public key encryption and also certs. Certs are going to be today as well. Tomorrow we'll talk about symmetric key encryption as opposed to public key encryption, which we'll talk about today. Key exchanges and certificates and certificate authorities we'll talk about today. But Wednesday is going to be the TLS part of this. We're going to talk about how we're going to use these encryption schemes to actually enable TLS, which is going to give us our HTTPS. So we won't get all the way to HTTPS today. And then Friday is going to be chock full of examples. I want to walk through how to generate a cert, how to install a cert, and make it more concrete. Whereas today, especially, is going to be more theoretical, more of the background material. And by the end of the week, we'll have a good understanding of HTTPS, or HTTP over TLS, or formerly HTTP over SSL. All right, so let's talk about encryption. What even is encryption? You know what I don't have right here is I don't have quick access to a clock. I gotta watch the time. If I go over, somebody stop me. And I should probably mention. I mentioned it in the email and on Piazza, but I'll try to keep the lecture content itself in the 10 to 10:50 range. But I will stay on until at least 11:30 every day, just interacting, answering questions, and effectively having a recitation-style review session after every lecture. I usually stay after every lecture and answer quick questions from students. I want to have some way of retaining that at some level, even if it's not one-on-one questions. It'll be group questions, but that'll be something I want to be able to do to get more of that interaction. All right, so encryption. So with encryption, we want to hide our messages. We want to be able to send our messages, but in a way that only the intended receiver can read. So we have some plain text message that we want to send. And plain text in cryptography just means anything that's not encrypted. So it's not necessarily the MIME type text/plain. It's just anything that we want to send that's not encrypted. So this could be our HTML, our CSS, our JavaScript. It could be WebSocket frames. It could be anything that we want to send. Raw bytes of an image, whatever it is. When we say plain text in this context, we just mean any bytes that are not encrypted. And we'll always encrypt at the byte level, where TLS is sitting right on top of TCP. TCP is just handling bytes, the internet, the wires, the Wi-Fi, that can only handle bits and bytes. So all of this is happening at the byte level. So everything has to be converted to bytes, and then encryption can start being applied. So we're going to encrypt the plain text to create the ciphertext, which I realize I mixed the spelling. Sometimes I do a Y and sometimes I do an I. I forget which one is the proper one. But I use them interchangeably. I'll have an example later where I have CI, but I just noticed that before lecture, so I don't know which one's the right one anymore. Anyway, so nobody should be able to read this ciphertext except the intended recipient. So anybody sniffing packets in the Wi-Fi, anybody reading all those packets out of the air, is only going to get the ciphertext. We want the property that with encryption that nobody can read the ciphertext except the intended recipient. So anybody reading that information out of the air gets nothing useful, no useful information. The intended recipient can get the ciphertext and decrypt that back to the plain text message. That's the property we want. That's the fundamental feature of encryption that we want. So if we have some message that we want to send, we're going to encrypt it. We're going to send this jumbled looking mess of garbage over the air. And then the recipient is going to be able to decrypt that, and only the recipient is going to be able to decrypt that back to its original message. That's what we want. And we want to make sure that this is scrambled enough that nobody except that intended recipient is going to be able to read it, which is the big question of how do we do that? Because this looks nice and random, but so does base 64 encoding, like we saw earlier. If this is just a string base 64 encoded, it's going to look random, but it won't be random at all. It'll just be an encoding. If we sent strictly bytes instead of decoding to ASCII or UTF-8 characters, if we just sent the bytes of an ASCII message, that's going to look pretty random too. So we want to make sure it's actually unreadable to another user, not just looking random. Which can be a common misconception. It's a common misconception out there. If something looks random, well, there's no way you can decode it. Well, it might just have a standard encoding with a standard decode like UTF-8. We don't want that. So we want to make sure that's actually unreadable to anyone except the intended recipient. So how do we do this? Today we're going to look at something called public key encryption. Specifically, we'll look at RSA, one public key encryption crypto system. With this, we're going to generate a public key and a private key. We're going to use the public key to encrypt a message. And the public key is, as the name implies, completely public. Everyone can read this key. Everyone gets to know what this public key is. And the private key, as this name implies, is kept private by the person who's going to be the intended recipient of these messages. So they keep their private key private, share their public key with everyone. And when somebody wants to send them a message, they're going to encrypt with their public key, and they're going to be able to decrypt with only the private key. Only the private key can decrypt that message. So as long as that private key is private, only that recipient can read that message. These are the features we want. It's a big question of how to get there. So these keys are inherently and mathematically related to each other. So there's one big concern that has to be addressed. If an attacker has the public key, which they should have access to, it's public, everybody's able to access that public key, they shouldn't be able to determine what the private key is. Now, these are mathematically linked together, so there is, I'm a little hesitant to say always, but screw it, I'll say it. There's always a way in any crypto system, any public key encryption system, to be able to generate the private key based on the public key, because you can use the same algorithms that were used to generate both keys and run them in reverse in some way to be able to generate that private key. There's going to be some way to do that, so we add this clause in a reasonable amount of time. There shouldn't be in a simple, straightforward, efficient way to compute the private key given the public key. And our fundamental feature of encryption, if somebody has the ciphertext, they shouldn't be able to decrypt it without the private key. If we don't have that feature, what are we even doing here? And of course, with the clause in any reasonable amount of time. Because with infinite time, infinite computational power, both of these are false. Where an attacker is going to be able to do both of these things given enough time. And in encryption, enough time typically means the sun will burn out before somebody's able to compute it. That's the level of security we're talking about here. So a reasonable amount of time, that might be, 2 to the 100 years to be able to break these things. That's the kind of levels we want to talk about in a reasonable amount of time. If it takes like a couple centuries, we don't really want to rely on that for security. That's where we want to be with encryption. Because a couple of centuries, well, all it takes is computers to get 100 times faster, which has certainly happened many, many times over. Computers get 100 times faster. Now that's 2 years. That time gets cut down pretty quick. But if we're talking exponential number of years, 2 to the 100 number of years or so, once we're in that range, it doesn't matter how fast computers get. It's not happening. You're not breaking it. And yeah, math and theory. If you're into math, if you're into abstract algebra especially, this is a very fun topic for you. There's a lot of math and theory going to help us out here. So let's talk about an example of a public key encryption system, one that's still used, pretty old, but still used quite often out there today, is RSA, named after the creators, named after the founders of this crypto system. This is a public key crypto system with, hopefully, the desired properties. We'll talk about that in a second. There's really never a guarantee, at least not yet. In my opinion, there never will be. No guarantee that we're actually secure. But we hope. It's a pretty strong hope. Like, we believe it pretty strongly. But there's always that possibility that all of cryptography is broken. So we'll all wait and see on that one. So with this, we have three features: a way to generate a public-private key pair that are inherently linked. We can encrypt with the public key and decrypt with the private key. And here's pretty much the bulk of RSA. Here's the math that we need for RSA. This is how we generate keys. This is an algorithm, just step by step, that we could run through. If this probably isn't, you're probably a little far along the program to have this. But if you had me for 199 for my security, I only did that the last 2 years. That wouldn't have been you guys in there. But if you had me for 199, I actually make the 199 students run through this algorithm, generate their own public and private keys. So it's not too complex. But let me just step through this one step at a time. First, come up with 2 large prime numbers. And large is a very important word here. If these numbers are not large enough, we don't actually have any security. These have to be very, very large primes to be able to get the security that we want. We're going to take those 2 primes, multiply them together, and get some value n. We're going to compute the value lambda of n, which is the least common multiple of p minus 1 and q minus 1. Then we're going to choose some value e, which is both less than lambda of n, and the greatest common denominator of e and lambda of n has to be 1, meaning that e and lambda of n are co-prime. So e and lambda of n have to be co-prime, and e has to be less than lambda of n. How large is considered large? Definitely not 4 to 5 digits. These should be of the order of like kilobytes of bits. So a typical key size is 4K, so 4,000 bit, well, more than 4,000 bits of integers. You would definitely be overflowing ints and longs many, many times over. Very, very large numbers. And that's key to our security. Those numbers have to be large, because as we'll see in a few slides, if somebody's able to factor n down to these primes, there's no security. So if you had a 4 or 5 digit number, any one of us could write a script that's really only a few lines that would be able to factor n in a couple of milliseconds. So we don't want that. We want these to be large enough, thousands of bits long of int representations to be able to get that security that we need. Very, very large numbers. So if we have some e, and we get to choose this, it can be any e, but there are some standard choices for e. But e less than lambda of n and co-prime to lambda of n, any choice will satisfy this condition, but there are standard choices that are known to have the best properties that we have. If you choose a poor choice for e, you might not have the full security that we expect. And then compute d, which is the inverse of e mod lambda of n. And mod, if you haven't seen mod, it's the modulo operator, it's the percent sign in our code. In algebra and the math world, we write it out as mod like this. So now that we have these, was the minimum length required for the prime? There's no necessarily minimum length. It depends on the level of security you want. It's pretty standard now to use 4K key sizes, so 4,000 bit representations, but you don't have to have a full 4,000K. If it just depends on your use case. It's a trade-off between speed of encryption and the level of security that you have. But there's no standard minimum length for the primes. But to be safe, if you go with 4K, then you're gonna have nice security. But if you want to have that speed, you have a web server that's encrypting a lot of traffic, doing a lot of key exchanges, as we'll see on Wednesday. Some keys are not quite 4K. I'll show an example later today. I think the example is 256 bits, if I'm not mistaken. I don't know. I have to look at that when we get there. So once we have all this computed, we're going to share E and N as our public key. So everybody on the planet gets to know both E, our choice for E, and N, which is P times Q. Both of those are collectively our public key. And then D is our private key, that inverse of E mod lambda of N. That's our private key. And then we throw away P, Q, and lambda of N. We don't need those anymore. Those were just used to generate these keys. We don't need them after the keys are generated. So once we have these, we're going to encrypt some plain text message M by raising M to the power of E mod N. And that's it. That gives us our crypto text. That's what we're going to send over the wire and over our Wi-Fi. Excuse me. And to decrypt, the intended recipient is going to receive C, raise it to the power of D mod N, and that's going to give them their original message back. So once we have these keys generated, encryption and decryption, the equations at least are pretty straightforward. It's one exponentiation and a modulo operator, which are actually fairly expensive operations computationally, but for our understanding, not too complex. So the way we set up these keys, we get this property. This is why the encryption works. M raised to the D and E and D modulo N is going to bring us back to M. So since E and D are inverses of each other mod lambda of N, and the way lambda of N is constructed, we get this really nice property, which the proof, it takes a bit of linear algebra. If you're interested, it's a neat proof. But M raised to the E times D mod N brings us back to M. The second one, prime miniature. M raised to the E mod N. E mod N, E is going to be less than N at all times, so E mod N would just be E, and it'd just be M to the E. It's the exponentiation and then the modulo operator. So with this property, we can actually do something really neat with public key encryption, or at least RSA, not necessarily all public key encryption by the definition. But we can do something really neat here. So M to the E times D mod N brings us back to the original message. So if we want to encrypt, we raise M to the power of E, the public key, mod N, send that message, and then raise that M to the E, raised to the D. By our property of exponents, we're going to multiply the exponents. That's going to give us this equation, and we're going to be back to M. So that's how we can encrypt, then decrypt. But multiplication is commutative. So we can, so it doesn't matter the order in which we perform these. If we raise it to the public key, then the private key, which we're doing with encryption, or raise it to the private key and then the public key, we're going to get back to the original message either way. So what we can do, what someone with these keys set up can do, is raise some message to the power of their private key, and then send that message out, and then anybody can decrypt it with the corresponding public key. Now, there's absolutely no privacy gained by this. Everybody on the planet is able to access your public key. So there's no privacy here because everybody can decrypt this message. So there's no privacy gained here at all. But what we do get is a guarantee that the person who sent this message is in fact the person with that private key, which if they're keeping their private key private like they should, we can verify that they are actually the person they say they are. So this is what we call a signature. If you've heard of a digital signature or cryptographic signature, this is what's happening. They're encrypting something with their private key, and then anybody with the public key can verify that they are the legitimate author and that this message has not been tampered with. So this is a very convenient property to be able to have. So anything we need to sign, raise it to the power of your, basically encrypt it with your private key. You don't gain any encryption, you don't gain any privacy, but you do get that verification. So there's one problem here. What about brute force attacks? I mean, there's a lot of problems. We can talk about a lot of them, but this is one I want to highlight. So we'll talk about it when we talk about hashing. What about a brute force attack? So if an attacker has your public key, which they should, it's public, and they have some crypto text that you just sent to somebody, what's stopping them from just guessing a lot of different plain text messages, encrypting each plain text message until the crypto text matches the crypto text that they recovered? This can be especially effective if, say, you're sending a Boolean to somebody. They know that the value is either going to be true or false, or 1 or 0, or whatever. There's a very small number of guesses that they have to make. They can just encrypt each possible guess and just see which one matches. This is a very concerning attack when we'll talk about in 2 weeks when we talk about handling user passwords. We're going to hash those passwords, and we need to protect against this attack somehow. When we talk about hashing passwords, there's really no good defense against this, though. There's not much we can do. Our solution right now is to tell our users, use a capital letter, use a lowercase letter, use a number, use a special character, at least 8 characters long. We have all these rules just to make sure it's hard enough for somebody to guess, because this attack is a valid attack for a password when we're using hashing. With encryption, we can actually get around that. And I'll talk about that more, the attack on passwords, when we get to that part of the class. And with encryption, though, we actually have a very strong, very secure way of handling this. We're just going to add a bunch of random bits to the end of each message. Done. That's it. So we're going to add a bunch of random bits to the end of a message every time we encrypt a message. And now when an attacker tries to guess that plain text, they have to guess the plain text plus all the random bits we add. We're going to add enough random bits so that's infeasible for them to guess them all. If we add 80 random bits, that's 2 to the 80 that they extra guesses that they have to make, which is, again, longer than it's going to take for the sun to burn out. We're talking ridiculous numbers. With the power of exponentiation, 2 to the 80 is some ridiculously huge number. Absolutely crazy number. Something that, if you want to have some fun someday, just try to wrap your head around how large of a number 2 to the 80 is. It is a ridiculously large number. So no attacker is going to be able to guess that in any amount of time before we're all long gone. So this does add security. Those bits have to be guessed, because when somebody decrypts this message, when the intended recipient decrypts the message, they just ignore those random bits. This is something that we can't do. We use something called salting in passwords that it's kind of similar, but with salting, we can't get that feature because we never decrypt, I'll put my quotes up there. We never decrypt a password. So that doesn't work. But again, we'll talk about that when we get to hashing and passwords. So even if we are just sending a single bit to somebody, this padding gives us actual security. So encryption is legit secure, as long as there's no breakthrough in math that breaks everything. So let's talk about that potential breakthrough. we have this key generation technique, and if we have P and Q, E and E, we can easily compute D. In fact, that's how we computed D. We had started with P and Q and just ran through the algorithm, chose our E, which if E is given to us, our choice is already made for us, and we can compute D the same way that just key generation naturally happens, right? Well, everybody has E and N. So to get E, P, and Q, all you have to do is factor N. Once you factor N, there's no security anymore. You can compute the private key. Does anyone know how the person with the private key can differentiate between the padding and the actual message? You'll add some extra bytes to the message to that and say this is how long the padding is. That'll all be part of the encryption that you do. So you can say, okay, there's the first thing. I don't know the exact format, but it'll be something like the first few bytes of the crypto text, of the plain text of the decrypted message is going to say there are this many bytes of padding, and then you ignore that many bytes, and then the rest is your message. So all you have to do is factor N, and security is broken. And for Apple, if the audio cut for you, I will, the recordings will still be posted up on YouTube. If you do ever miss anything, make sure you can still go back and get the full recording. I'm gonna stream and take the stream. The stream will be on Twitch, but I'm also recording locally. So even if my network cuts out, if I lose internet or anything else happens, I'll still be able to get a recording up later. But I don't. Well, we'll just see. So all we have to do is factor N, and the encryption scheme is broken. So luckily, factoring is hard. We hope. We hope factoring is hard. If factoring is not hard, RSA is broken, and so is a lot of other cryptography. So there's actually no known algorithm, not publicly known anyway. It's possible that some attacker somewhere in a bunker somewhere has an algorithm, an efficient factoring algorithm, but it seems unlikely. They would be able to do a lot of damage really fast. It seems unlikely that they would have that and not do much with it. But that's speculation. There's no publicly known algorithm, because as it turns out, factoring is a very difficult problem. At least it's turning out to stump the mathematical and computer science communities at large, and how to come up with an efficient factoring algorithm, specifically when the factors are two large primes. We just don't know of an efficient algorithm to do this. So if you can come up with an efficient factoring algorithm that can factor the multiplication of two primes, and those primes are thousands of bits long in their representations, I don't even know what you should do. Probably contact the RSA and not RSA. I just saw RSA. I'm blanking on it. Or whatever you want to do with it. Maybe keep it to yourself and break a bunch of shit. I don't know. Whatever you want to do. Or tell me, I'd be interested. So it hasn't been proven that this is actually a hard problem, so we don't actually know. There are a lot of problems. Actually, no, there's not. There are some problems that we've proven that can't be computed. I guess there are no problems that we've actually proved that are hard. But I don't want to go down that road. If you're interested in that, take 396. They'll talk all about it in that class. But we haven't actually proven that these are hard. There's no proof that says you can't factor efficiently. But we don't have an algorithm that can do it. So it's a big unknown. The common belief is that this is a hard problem, and it touches on the P versus NP problem. It's not exactly that. Factoring is not an NP complete problem, but I'm getting sidetracked. Anyway, I could talk about that for a while. If you're interested, we could talk about it during the Q&A. But we do believe that it's hard, and we call this a cryptographic primitive. If you build a crypto system and it and you have proofs and everything that says breaking this crypto system would imply that you've factored efficiently, then you have a secure crypto system. So once you've proved that breaking your crypto system is the equivalent of breaking a cryptographic primitive or efficiently solving a cryptographic primitive, you got a secure system at that point. At least the community is going to accept it as a secure system. If you can't do that, if you don't prove that it's the equivalent of breaking a cryptographic primitive, nobody's going to take you seriously unless you propose that as a new cryptographic primitive. That's tough to do. So there's also another vulnerability. Is factoring in NP? Yeah, I don't want to go too far down that road unless you want to talk about it after the lecture portion. But it's in NP, but it's not NP complete. So if you factor efficiently, that doesn't mean that P equals NP, but it does have other implications to the hierarchy. It does collapse part of the hierarchy, but it doesn't go all the way to P equals NP. If I remember it right, I'm like 95% sure on that. But I know it's not NP complete. Yeah, if it's not NP complete, then it can't collapse the whole hierarchy. I'll shift that to 99%. Do you choose the primes from a list or do you compute them? In practice, I'm not positive how they're generated. But as long as you get two big primes, if you have a list of primes that you want and you just randomly choose one from that list, I don't see how that'd be much different than computing them. The list is basically pre-computing them. So either way, it'd be effectively the same. But in practice, I'm sure there are a lot of important choices that go into which primes you choose. I'm not familiar with that side of it. So there is another problem here. If somebody takes some crypto text out of the air, and they have N because it's public, and they have E because it's public, all they have to do is find the log of C base E mod N, which is what we call the discrete log problem. If they compute the discrete log of C log E mod N, they have the original message. So this is bad. Once they compute the discrete log, that's bad. Lucky for us, we also believe computing the discrete log is a hard problem. This is another cryptographic primitive. If your crypto system, breaking your crypto system implies solving the discrete log problem in an efficient amount of time, again, you're secure. So we're actually good on that front as well, thanks to our cryptographic primitives. So let's see. I mean, we're at 10:50. Let me do a quick Java demo, mostly because I want to test this aspect of my stream setup. Let's see a quick demo of this, and then I'll cut off the lecture portion. We'll go into some Q&A. But let's switch to IntelliJ. Let me reorder some windows here. Hey, it's pretty seamless transition. All right. So let's look at some Java code and see how in Java you do some cryptography. And just note for the homework 7, this is not the level that you would have to do this. I'm just doing this to show off some RSA in some code. You wouldn't have to be generating your own keys, necessarily not like this at least. You will generate your certificate, which is similar. It will involve generating keys, but it'll happen behind the scenes where you wouldn't have to get down and dirty to this level with the revised homework. So with this, we're going to generate a key pair. Java has all this built in. These are all Java libraries. I'm going to pull my key pair generator, get an instance of RSA, generate the keys, and just return that key pair. To encrypt, I'm going to create a cipher. I'm going to encrypt the bytes of a message. So I'm taking a string. I'm going to convert that to bytes. Our encryption is always working in bytes. Get the encrypted bytes, and I'm going to base 64 encode that just so I can print it to the screen and show that it's a jumbled mess of stuff. Even though that won't prove anything, you'll have to trust that with the RSA being applied, that nobody's going to be able to read that without the private key. Then a decrypt, basically the same thing as the encrypt, except I'm going to use decrypt mode. Base64 decode the message, get the bytes, and then convert the bytes to a string. So, using that example in the slides, we have this message that we want to encrypt. I'm going to generate my key pair. I'm going to get the public and private keys out of that key pair, just so I can show them separately, sort of in two separate variables. I have my message that I want to encrypt. I'm going to encrypt it, the same exact message twice with the same exact public key to get two different ciphertexts. I'm going to print those to the screen and then decrypt both of those ciphertexts with the private key to get back to the original message. So if I run this, we'll see that the ciphertext for each of these, a very long, random looking, but of course has a very, not predictable, but very structured pattern because it can be decrypted, and we decrypt back to the same message. But what I want to point out here is that when we encrypt the same exact message two separate times, we're getting very different ciphertexts out of this. And that's because we're using a padding algorithm to make sure that we are getting different ciphertexts each time, because we're adding padding to each plain text message before we encrypt. So the same exact message sent twice, but two different ciphertexts. And this is very important, even if they're not brute forcing our crypto text. If they keep seeing the same ciphertext being sent over the wire, that's going to clue them in that we're sending the same message each time. And then they can start building information. They can start figuring out what we're doing at that once we start leaking any form of information. If there's two different messages that keep being sent, they can guess that that's a yes-no response. They can start just starting to try to piece together what's going on there. We don't want any of that. We don't want them doing that. So we use the padding scheme, which is going to prevent that from happening.